Hi, good morning. Hope everyone's doing well. I'm Damian Brady. I work for GitHub, St. Patrick's Day, so I wore my green shirt. I work in the developer advocacy team at GitHub, and I'm not really going to talk about any of that today. Instead, I'm going to talk about DevOps and how it applies to machine learning. So unless you haven't looked at the internet for the past, few months, you probably... if you haven't looked at the internet for the past few months, you won't have seen all of the announcements around AI kind of almost crossing that chasm. I don't think it's actually crossed the chasm. I think we're still in the early adopter stuff. But there's a lot of things in there that are going to suddenly jump it over this chasm because it's going to be embedded in all of these tools that everybody uses all the time anyway, right? It's a little bit like forcing the new technology onto the iPhone that you already have, and it just becomes part of that workflow. They get a little bit of a shortcut there, I think. The reality, though, is that machine learning is going to become part of our day-to-day in terms of writing software as well. I'll talk a little bit about these large language models kind of at the end, because they have changed the game a great deal. But for the moment, we're at a DevOps days to a smaller or greater extent. Everybody here is involved in DevOps, in the process of like writing traditional software and software delivery from idea all the way into production. So I want to talk about how we can apply those skills to this emerging field and growing field of machine learning. So for those of you who are not familiar with machine learning and what it actually means, I want to do a little bit of a level set, and I'm going to do the world's shortest demonstration of what AI and machine learning actually is. So the short version is that when you hear somebody talk about AI and AI being part of their product, it's one of two things. Either it's machine learning, and that's how they've come up with this model that is called AI, or it's grift, and they're trying to take your money and there's no actual AI in there at all. And I don't know, 50-50. But AI, or machine learning, is how we get AI, basically. Now, for all of us who are traditional software developers, you kind of know how programming works, right? So you have, as a programmer, you have a problem. You write an algorithm, you write a function or something to solve that problem. You supply data and that algorithm to a computer, and it will run the data through that algorithm, the input through that algorithm, and give you an answer out the other end, right? And this is good for problems where we know what that algorithm can look like, or we can work it out. So as an example, what is the interest due on this person's loan for this last month, right? You have your inputs, which is the balance and the interest rates and anything else you need. You have your algorithm that you as a programmer know how to write. Here's how I calculate my interest. You run them through and you get an answer, and that answer is correct, of course, because you haven't written any bugs and things like that, right? So we know how to solve that problem. It's a step-by-step thing. But what about if the problem is not something that's so easy to solve? Like, rather than what is the interest due on this loan, what is the likelihood that this person is going to default on this loan? Like, how do you get that logic, right? And to use a bit more of an abstract example, the good old classic thing from the XKCD comic, is there a bird in this photo? What does the logic look like for determining whether a bird is in a photo? Like, it's very hard to explicitly write that logic out. And those problems don't go away. They still want engineers to solve those problems, and machine learning is how you do that. But you can't write that algorithm. You don't know what that looks like, right? You can make some guesses and maybe you'll get close, but you're not going to do a great job. So what machine learning does is it flips this around, and you provide a whole bunch of already solved problems, like already resolved answers. So here are all these pictures with birds in it. Here are all of these pictures with no birds in it. You supply those answers along with the data that goes with those answers, and then I'm going to completely gloss over the purple box in the middle. That's where all the training happens, and there's multi-dimensional calculus and stuff like that in there, so let's pretend it doesn't exist. But the computer works out what the patterns look like, and it develops an algorithm that links the answers that you give it with the data that you've given it. So it's created essentially a model to map, input with output. And that model is correct to a small or great extent. It depends how well your training worked. And this is really all we do. Now, in the example of large language models, because I know everybody's probably thinking about GPT, ChatGPT, and things like that, it's exactly the same thing. It's just that the data that you provide is internet scale. The training costs millions and millions of dollars on machines in the cloud with hundreds of GPUs in them. You can't do that yourself at that scale. But the answers are embedded in that. So they will take a sentence from the internet and they'll remove a word and they'll train the model to try and replace that word and try and get it as close as possible. Then they take another sentence and they remove a word and they get it to train on that sentence to try and get that word back in. You do that billions and billions of times and you'll start to get a model that represents how to replace words or predict what word comes next in sentences and things like that. Same thing, massive, massive scale. So we have this model, right, that describes the relationship between the answers that we've given it and the data that we've given it, right? The good thing about that is that model is essentially an algorithm. It's a function that you would have written if you knew how to write it. So we can replace that model with the algorithm that we would have written if we wanted to. So we provide that model and the data, the input, run it through, and we get a prediction. And note that that's a prediction, not an answer, because it might be right and it might not. Because the stuff that came out of that purple box, we don't really know what it looks like in most cases. There's a lot of math in it. You can trace it through with all your weights and balances and things like that, but we don't know what that means to a large extent. It's a black box. There's a lot of research going into trying to make models explainable, but it's a very hard problem because we compress all of that knowledge and the mapping for the answer to the from the input to the output, we compress this into this barely recognizable series of mathematical equations, right? And it's very hard to say, oh, well, there's a bird in the picture, and it says there's a bird in the picture because there's a beak there, and then there's like a tree, and birds often on trees. It's not like that. It's just weird math that tends to come up with the right answers. Anyway, I digress. This is how machine learning works, right? And you'll notice some kind of similarities to the way that traditional software development works. If you think about how that occurs. With traditional software development, we write some code, and then we work together to make that code solve the problems that we want. We pick up a ticket from the left, and we say, oh, we're solving this problem. We get some code that's working, we run it through a CI system, it builds, it tests, we know, okay, it's doing a really good job. We deploy it out to an environment, we monitor what's happening in that environment and whether it's succeeding. A lot of those ideas can get carried through to machine learning, but there are specific areas where it's very different. And I want to talk about those areas a little bit. I don't know how many definitions of DevOps have appeared on the screen. Let's just agree that there is a general idea of getting valuable stuff from an idea into production, right? One thing that none of these definitions show is, or include is taking a ticket from the left-hand side of the column to the right-hand side of the column. Or DevOps is about fixing a bug or delivering a feature. It's none of that. Those definitions never include the specific bit of work. It's all about delivering valuable solution-solving things to a user, right? And because of that, any kind of software or any kind of delivery of value really can be applied when you look at the DevOps definition. So DevOps can apply to any type of delivering value to your end users, from an idea to valuable. My point is that the existing definitions of DevOps, what we do, absolutely applies to machine learning problems. But let's talk about some of the differences. So some of the things that MLOps is going to try and solve or needs to solve are slightly different. So source control and making sure we version the work that we're doing, really standard with traditional software development, a little bit less so with machine learning, so we're starting right from scratch here. Versioning the models that you produce is something that a lot of data scientist teams do this, but they don't have the tooling to do it very well unless they've already adopted some of those tools. So we'll talk about model version tracking and what's important there. Experimentation is a huge difference between traditional software development as well. So I'm going to drill into that a little bit more. Validation and testing has its own challenges with machine learning, particularly because we're not writing that algorithm where we can prove, oh, look, it goes through this code path. we get the right answer at the end? We don't know. So testing and validation has its own challenges. Deployment, pretty similar, but there are some unique aspects to machine learning deployment as well. And then finally, monitoring performance and efficacy are really, really important with machine learning models as well. But our existing DevOps knowledge can apply to a lot of these things anyway. So let's drill into these. Source code. Now, you do need code to train machine learning models, right? There's a lot of iterations of getting data, doing some stuff with it, and spitting it out. But there is a lot of code involved, usually Python or R or whatever, other language, right? So that code should exist in source control, of course. The definitions of the infrastructure that are required both for training and also for the inferencing, for running it in production, should also be in source control. Exactly the same as keeping our development environment definition in a dev container or something like that. That's a great thing to keep in source control. Versions of what Python you're using, of what Python libraries you're using, and things like that. And then also what needs to exist in production to be able to serve that model and do the inferencing in real time as well. It needs to be in source control. That's fine. But data can be really, really big, right? So those large language models basically absorb the internet and do training on the internet. How do you version that, right? Obviously not in Git. It doesn't do a great job with data of huge sizes. There are some tools that can be used for this. So DVC is one of the ones, classic ones, data version control, and it's a Git-like system, but kind of acts as a proxy, I guess, to other files. Pachyderm is another one that has that functionality of versioning data, and Azure Machine Learning. The important things here as well is it's not just that massive corpus of data that you're training on. It's all of the feature selection, all of the data processing that happens beforehand. All of that kind of stuff needs to be versioned as well. And that's largely code. You know, I'm going to run this code to take out the outliers in there. Or I'm going to run this code over this gigantic internet database to remove all the references to bomb making, for example. Like that might be part of your data processing as well. So those things can be versioned. But then if you think about models that use imaging. So I was talking to somebody the other day about medical imaging AI. That data set of all of the scans, the medical scans, you need to version that when you get new information in and realize that a particular image shouldn't be in that data set anymore. You need to be able to version those data sets as well. So there are tools that can let you do that, but letting data scientists know that you have to version this stuff, otherwise it's not reproducible and it's not traceable, is really important. Model version tracking. So when you've actually produced a model, being able to determine not just that this is version 2 of the model, right, but a lot of the metadata around it. What did the data look like that I trained it on? And in some cases, you really, really need that. If you make a financial decision for one of your customers based on the model, based on an AI model, can you go back and say, well, this is the data that we had on you at the time? Or are you going back and saying, well, this is the data we currently have, but it's probably not what we trained the model on? That's probably different, and I don't know what that looks like. So you need that metadata of this is what we trained the model on. But also metrics, things like how accurate that model is, how many false positives, what types of false positives there are, and performance as well. And these are important because you might need to go back in time and say, well, this new model performs really, really well on this subset of data, but it turns out we have this horrible problem where we get a lot of false positives for this demographic. What changed between this model and this model? Oh yes, I can see those metrics changed at that point. What did we do to change the training of that model? Okay, maybe we need to reproduce that and do a similar thing to get a better performing model. So all of these kind of metrics and measures around what that model does and how it behaves are really important to track as well. Experimentation is a big one. So in data science, in machine learning, it's not a linear progression. So you don't, version 2 of a model is not version 1 with these extra 3 features. It doesn't work like that. Part of the problem is that you don't know to some extent what's going to come out of a training run. You can do a training run, you can filter the data and say, I think this is going to produce better performance or better efficacy, and so we'll do a training run. But then what comes out the other side is like, oh, well, it kind of does, but then it's totally dropped the ball on this area here. So rather than this linear progression of more and more features and bug fixes and things, you get this constant branching of ideas where most of them get abandoned and some of them continue. But it means that that linear progression of version 1, version 2, version 3 doesn't really happen. Experimentation is a big, big part of what happens in machine learning. So you need to be able to enable that experimentation. Along with that as well is the difficulty that machine learning training runs can be very expensive. So you don't want to have to do them every single time somebody has an idea, a full training run. Can you imagine with the GPT ones, those large language models that take weeks on, millions of dollars of compute? If somebody says, oh, maybe if we try and remove this data, I'll just fire that one off. Like, you're going to burn money quicker than anybody, right? So you need the tooling to enable experimentation. Now, some of the tooling, I keep talking about Azure Machine Learning because that's the one I'm familiar with, but a lot of the tooling has the ability to cache results at different stages. So you don't have to rerun the entire training run. You can rerun just the bits that failed. Now, I don't want to get into that too much because that's very particular to the tooling and it's very particular to how machine learning works. But understanding the concepts of being able to fire off training runs, phased training runs as well. Can we run this training over a small subset of data just to make sure it's doing the right thing? Okay, that looks promising, let's move it to the next phase to do another larger training run, test it against our data and things like that. Those practices of having that pipeline to actually build these models and deploy them at the other end is something that, as DevOps engineers, we do all the time. We understand how that works, but it's not something that machine learning experts and data scientists know how to do. So building those tools and helping people use those tools to be more effective when they're doing their experimentation is a hugely valuable skill that you can bring to data science teams. The other thing with experimentation is all of these experiments are generally working towards something like a good result, something that is close to what we want the machine learned model to produce, right? But then what is good? In some cases, it's really easy to determine what is good. So let's think about like a translation AI. So it translates from English to Spanish, for example. It's relatively easy to determine whether one model is better than another model. One experiment has performed better. You might train on a gigantic corpus of human translated phrases, right? So you feed them in, you get a translated result, and you can compare that to the human translated phrase. You can determine, okay, this one translates more of them more effectively than the previous ones. But even that's not so easy. Imagine you produced a model that gets one really common English phrase wrong every time, but not much else wrong. Is that better? Is that a better model than a different one that gets that one right, but tends to fail on less common phrases? Which one is a better model? So it's hard to work out whether something is good even. The main way to do it is to test in production. So we talk about testing in production in traditional software development, and everybody giggles and, all right, yeah, of course we test in production. I mean, everybody tests in production. It's just, do you have test environments before production as well? So testing in production is absolutely vital in machine learning. You can test to some extent with your test data and your training data and things like that, but you never really know whether it's going to perform that task effectively with real production data. The only real way to know is to deploy it. So while in traditional development we might just throw out an application and write over the other one because we're pretty confident it's the same as the previous one plus a couple of features. If we're really, advanced, maybe we do some canary deployments, or maybe we even do some A/B testing. And those techniques are really useful in machine learning. A/B testing gets used constantly by all of the large players in the AI field. They would deploy 2 versions and slowly move traffic to one and determine how it performs versus the other one, and maybe even identify things like, for this demographic, this model performs much better than the previous one, but it completely drops the ball on a different demographic, so maybe we'll split our traffic based on who's visiting the site, give them different models for different areas. The other technique that gets used is one called ghost deployments, and that's where you actually deploy both versions of your model, and you run it through the one that's already in production, but you also run the input through the one that you are thinking about deploying, that you think is doing a good job. You look at where the differences are and you analyze those to work out, oh, this is actually probably performing better. That's also really good for performance testing. A model that does a really, really good job but takes way too long to do it is a terrible model. Right? If you were using the announced last night, like Microsoft Copilot for Word or something like that, and every time you paused to get it to write the rest of the sentence, it took 20 seconds, you probably wouldn't use it, right? Because it's just going to take too long. So it might be really good at producing that output, but it takes too long to be usable. So ghost deployments are great for that kind of stuff as well. So A/B testing and ghost deployments are really, really good for that stuff. And it's also important to realize what you can feasibly learn. So the difficulty with testing in production with machine learned models is unless you have a large volume of data going through your models, and that data is representative of what people are doing in production, you may not be able to learn that much. So if you have 1 or 2 requests a day, and you see that, oh, people aren't clicking on my recommendations as much, but you only have this tiny amount of data, it's really difficult to make decisions based on that data. And that's why if you go to like ChatGPT, you get this message right at the start saying, hey, this is a trial thing, and we are using your responses to determine how good the model is. And they use that training to work out, what models are performing better and what features are performing better. So when you get an answer, there's actually like a thumbs up and thumbs down. I don't know if anybody's ever clicked them, but the idea with those is that it can learn what the good responses are and what the bad responses are. And this is using a technique called RLHF, or reinforcement learning with human feedback, which is a really great way of doing it. Sometimes it's really easy to get this. So if you're doing a recommendations engine for a store, like an online shop, and you say, hey, you bought these things, here's some recommendations, the human feedback can be literally how often do people click those recommendations. And if they click them more, then that's a good model, right? It's doing better. Sometimes it's really, really hard. Copilot, GitHub Copilot, uses this kind of idea to determine, like if you get that ghost text suggestion and you hit tab, that's reinforcement to us that that was a good suggestion. There's more stuff we do around that, but I'm not entirely sure how much I'm allowed to tell you. But there is reinforcement learning that happens as a result of the way you behave against these models. So that kind of stuff is really handy as well, really useful for improving machine learned models as well. All right, one last thing I just want to talk about, which is the idea of drift. And there's 2 types of drift. There's model concept drift and there's data drift. Model concept drift is when your idea of what the model should do differs from, it differs over time or changes over time. So as an example, imagine you have a model that does credit card fraud detection. So anomaly detection with all the transactions that are going through. The bank may decide that they have changed their definition of what actually constitutes fraud. And it turns out that these things that it previously considered fraud, not really fraud. Maybe we're allowing people to buy crypto now, and that's fine. That kind of changes the concept behind the model, that business case behind the model, and you might need to rethink how that model is trained. Data drift is kind of similar, except it's more the idea of your model going stale. The simple version of explaining it is that the data that you trained that model on no longer represents the data that is seen in production. And this can be because just over time it goes stale, people are using it differently, or the world has changed. Or it can be seasonal as well. So if you have an online store, your recommendations engine might perform really, really badly leading up to Christmas because people only want suggestions for Christmas-related stuff. That needs to be an indication that your model needs some retraining. So that idea of observing how it's being used in the wild and being able to trigger a retraining or a tuning or something like that. Now, again, some tooling is really good at doing this. Keep talking about Azure Machine Learning, but Azure Machine Learning has drift detection where it will analyze the production data and the training data, and when it reaches a certain difference threshold, it will actually trigger a rebuild and then retest with the production data and say, okay, now it's actually reaching the metrics that we wanted it to, let's redeploy. And deploy a canary deployment, see how that performs, and so on. So you can do a lot of that stuff automatically with this tooling. So these are some of the ideas that are important with machine learning and machine learning projects. And hopefully, while I've talked through those, you've been thinking, oh yeah, okay, we do a similar thing, or we've talked about a similar thing with A/B testing, or with the multiple phased pipelines or something like that. So those skills that you have in traditional software development can be applied to this machine learning practice as well. I just want to touch on one more thing before I go, and that is that generative AI has completely changed the game. The last time I delivered an MLOps session was actually a couple of years ago, and this wasn't even, this wasn't top of mind at all, right? But it seems like suddenly ChatGPT was the main trigger here. But these gigantic large language models that have this almost emergent behavior, these are just trained on what is the next word that I should put after the ones you typed. But it has this almost emergent behavior of kind of understanding what you're getting at and giving you very human-like answers, which if you think about how it's trained, is kind of, I don't know how that works. It's very, I don't know, it's somewhere between impressive and really disturbing, right? But that's changed the game a little bit because you can't retrain a large language model whenever you have a new idea, right? Famously, the GPT models, the state-of-the-art GPT models, cost millions and millions of dollars to train, right? I actually had a chat with the GitHub Next team, who is responsible for GitHub Copilot, and asked them what their process looks like. Naively at the time thinking, oh, you make some tweaks to the code that you're using as the data, and then you do a retrain, and maybe that costs a few $1 million. And they're like, no way, there's no way we can do that. So they do training around the edges, where the core model, those GPT models, are used as the base. And then you just do some tuning over the top. Now, you, as a consumer of a GPT model, even with ChatGPT, prompt crafting can give you dramatically different results. So what information you give these models can give you incredibly useful results, or you can kind of poison the input with stuff that will give you terrible results. And we get into the whole jailbreaking of GPT thing there, where you try and get it to do things that it's not supposed to do. Now, GPT-4, they announced that the size of the input that you can give it has moved up from 4,000 tokens, which is probably about 2,000-3,000 words. Sorry, about 2,000-3,000 words, to 8,000 tokens that you can give it as your input. But they've also said that there's a 32,000 input version of this GPT model, which means, for those of you who did English at school, you could hypothetically, as the input, put the entirety of 12 Angry Men, the play, which is 24,000 words, as the input, and then ask it questions about what that looks like. Or you could put in some examples of really good code that you want it to generate, and then say, okay, now generate me code that does this. And it will use those examples to give you really good results. Now, my point here is that to a very large extent, these large language models that somebody else spent millions and millions of dollars training can be used as this basis for almost anything, provided you do some really good prompt crafting and give it some really good seeded information. And you can start using these as your AI in whatever application you have. the process for building those really good AIs based on these base models may not need massive amounts of retraining. It may just need some experimentation with how you do that prompt crafting, what information you give it to get the best results, the way you ask the question to get just JSON in your response, for example, so you can use it directly. But regardless, these processes of, hey, we've got this idea, we're going to make a change to the way we generate our prompts, and then we're going to try that with a whole bunch of our test data, see if it works, see where it fails. Okay, here's another idea. Maybe if we tell it explicitly, only give me JSON in a code block, and then see how that performs. That process still runs through exactly the same way, and it's a little easier to understand. Right? So regardless, that MLOps process, all of those things that I talked about, are still really relevant. So I just want you to have a think about that, applying the knowledge that you have in DevOps to this growing field of machine learning. And if you're looking for new opportunities for places to work, think about that as a future area. Thank you. I don't think we have time for questions, but I'll be around all day, so thank you very much.